So on quiz 0, one of the series of questions I ask you for problem 10 is to draw the Lewis dot structure of a given molecule, label any atoms with non-zero formal charges, what is the electronic structure of the molecule, what is its molecular structure, what is the orbital hybridization of the central atom, and is it polar or non-polar? Obviously, that's a lot of stuff, but it's critical because as you look at a molecule, these are all things you have to think about. You know, obviously, what's its structure? Does it have single bonds, double bonds, lone pairs, so forth? What does it look like in 3 dimensions from an electronic point of view? What does it look like from an atom point of view? Because those 2 geometries are not necessarily the same. This gets us into VSEPR, valence shell electron pair repulsion, as well as a little bit of valence bond theory with the orbital hybridization. Chemical bonding, again, we start with Lewis dot structures and then we start working our way up. I haven't talked about ionic bonding because that should be trivial at this point for people at the 200 level courses. But Lewis dot structures don't give us all the information we need. So that's why we need these more advanced theories. So I have several molecules listed. I'm not going to go through every single one of them as far as these videos, but I've got a few that I'm going to pick and choose and work through them. And again, you should be doing the same thing. And if you get stuck, obviously you can email me, but I would highly recommend go back to your general chemistry notes, reread the sections on chemical bonding, VSEPR, valence bond theory, and fill in those gaps and try and do it as best you can, because that's the best way to learn. You really have to just go at it and redraw the same structure until you're comfortable with it. Okay, so NOCl3, nitrogen oxytrichloride. Again, by convention, the first atom is the central atom. Now, before we worry about that, we can just, off to the side, count up the valence electrons. So nitrogen has 5, oxygen has 6. We have 3 chlorines, each that have 7 electrons. So that's 21. And so if I do this math, hopefully, correctly, that gets me to 32, 11 plus 21. Now, again, the drawing that I'm going to start with does not necessarily correspond to the 3-dimensional structure of the molecule. But we're just doing a Lewis dot structure. So there are my atoms. And again, the relative position of the oxygen for the chlorines doesn't make any difference. From my experience, my point of view, when I have a unique atom, I tend to put it like kind of, you can think of this as a compass in the north position, right? North, south, and then, you know, east and west. It doesn't matter, you know, up, down, right, left, whatever. You could draw this askew, it's not going to matter. But what does matter is how we put the electrons in. So we have 32 to work with. Everything has to be bound together. 2, 4, 6, 8. So those first 8 electrons are purely for binding the molecule together. Well, obviously, the terminal atoms do not have an octet, but if we look carefully, we can see the nitrogen actually does have an octet from these 4 chemical bonds. So that's a good sign. Now what I'm going to do, I have 24 electrons. I'm going to put them in as lone pairs and then go from there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 and 24. Obviously, you don't have to count aloud as you put them in. So 24 electrons, well, I put in 24 electrons, and as it turns out now, if I look carefully, I can see we got 3 lone pairs on each of the terminal atoms, and that gives each one of these atoms an octet, right? So 2, 4, 6, 8, 2, 4, 6, 8, and so forth. So that's good. We've used up all our electrons, and we are obeying the octet rule. Now, the next question, label any atoms with a non-zero formal charge. All right, so with formal charge, I'll start with the chlorine, and in this case, all of the chlorines are identical, so the result will be the same. Formal charge is going to be the number of valence electrons that a chlorine atom has outside of the molecule, minus the number of electrons that it has either on itself or as sharing. So we have 2, 4, 6 from the lone pair, and 1 from the chemical bond. Again, we share from the chemical bond. So that's 7, right? 2, 4, 6, 7. So our formal charge is going to be 0 for the chlorine. And all 3 of them. What about our nitrogen? Okay. Nitrogen has how many valence electrons? Now again, even without a periodic table, you should be able to figure that out, or at least have enough experience that you remember that it's 5. Having you get more familiar with the periodic table is definitely something that's going to be a focus in this course, and I'll have it as an incentive rather than punitive. So we have 5 valence electrons for a nitrogen atom. In this molecule, however, 1, 2, 3, 4. The nitrogen only has 4 electrons surrounding it. So that gives me, well, 4 minus 5 is plus 1. Right? So we have a non-zero formal charge. The oxygen its formal charge, and it shouldn't be a shocker that it's going to be minus 1. Well, let's go ahead and convince ourselves that that's true. Oxygen starts with 6 valence electrons, a neutral oxygen atom. 2, 4, 6, 7. 6 minus 7 is minus 1. How did I know that? Well, the chlorines are 0. If this has a plus 1 charge, then there's got to be a minus 1 charge somewhere because the overall molecule is neutral, right? So again, this is something you should be actively thinking like that as you solve a problem, because it has to be self-consistent, right? So in other words, if you make a math mistake and you say, well, the nitrogen is plus 1 and the oxygen is 0, then that means this molecule would have an overall plus 1 charge, but it doesn't. So right there, again, those kind of things are really helpful to think about. Can we make the formal charge go away? If you recall, because I'm sure you've watched all the videos that I put on there, formal charge is a higher energy state. Having formal charge is a higher energy state than having 0 formal charge. So a non-zero formal charge, you have a plus and a minus. Well, to keep them separated, that is energy, right? Because plus and minus, they attract. They want to basically cancel each other out. That's basically the molecule wants to get to the lowest energy possible. But in this case, the way to get rid of the formal charge is to simply put a double bond here. Take this lone pair, put a double bond. But you can't do that. And the reason why you can't do that, I'll give you a moment. You can pause the video if you can't figure it out. Nitrogen. Nitrogen cannot violate the octet rule. If we put a double bond here, nitrogen has 5 chemical bonds. Octet rule violation. So in this case, we are stuck with a non-zero formal charge. We're going to see that in some cases, violating the octet rule to remove a formal charge is perfectly fine. In fact, that's what's observed. But in this case, the octet rule is preventing us from doing that. And again, this is something we'll be discussing the root cause of these type of things later in course. Basically, it comes down to what atomic orbitals are available. Nitrogen does not have d orbitals available to have more chemical bonds. When we look at this, the analogous molecule for phosphorus, where it's phosphorus oxytrichloride, we will see that this has a double bond. So, spoiler alert. I'm going to erase the board and start with the rest of the question in a moment. But again, if you don't feel comfortable drawing this Lewis dot structure by yourself, you need to practice. Again, watching me only helps you so much. Even if you watch all the videos, still take the time to rework every single one of these problems by yourself with just a periodic table, and that will help prepare you. Because again, just watching a lecture is not the same thing as really getting it sorted through in your mind as you do this kind of problem solving. Okay, so we have our Lewis dot structure, so I've redrawn it. Why the lone pairs are so low. Now, the next set of questions after formal charge, what is the electronic geometry of the molecule? What is its molecular geometry? What is the orbital hybridization? And is it polar or nonpolar? Now, as we try and answer these questions, what we have to understand is this Lewis dot structure, it gives me the connectivity of the atoms, who is bound to who. It gives me the order of the chemical bond. Is it a single bond, double bond, or a triple bond? We refer to that as bond order in a formal sense. Lone pairs as well, but it doesn't give me the three-dimensional shape. This is the valence shell electron pair repulsion theory. And I'm not going to go over that now. So again, that's something from Gen Chem you should review. So we have our nitrogen. It's the central atom. It's bound to 4 atoms with single bonds. So what that means is the electronic geometry is going to be tetrahedral. Abbreviated as TD. What do I mean by electronic? Well, if instead of, let's say, the oxygen atom here, let's say there was a lone pair on the nitrogen, we would count the lone pair the same as a bond pair. Now, there are no lone pairs on the central atom. So what that means is the electronic geometry and molecular geometry are identical. So they're both tetrahedral. A perfect example of where that's not true would be ammonia, NH3, or water, H2O. Both of those molecules electronically are tetrahedral, but their molecular geometries differ. Again, this is something you just gotta know. What can be a stumbling block early on in understanding molecular structure is being able to visualize the going from a planar representation of a molecule to what it looks like in 3 dimensions. And we have molecular models that are available. I'm going to draw something on the board in a second, but you really need to start getting it in your head by practice of what the representation really looks like. For tetrahedral, so all I'm going to do now is I'm going to redraw this molecule with perspective. So what I mean by perspective, the oxygen and this chlorine, they're in the plane of the board. So I draw the chemical bonds with just regular lines. But this chlorine, imagine that it's pointing out of the plane of the board. So this solid wedge means that it's coming out at you. This chlorine, okay, we're going to use a dashed wedge, and that means it's going behind the plane of the board. I did not ask it on this particular quiz, this problem set, but you should know the bond angles associated with the geometries. In the case of tetrahedral, ideal tetrahedral, these bond angles are 109.5. Again, this is something we will review going forward because it's very important to understand these geometries. In transition metal complexes, we can get a host of geometries. Tetrahedral is very common for certain metals, but we'll see octahedral is also common, and there are all kinds of geometries in between. So just something to keep in mind of review the VSEPR, valence shell electron pair repulsion. That, I believe, is chapter 7 in the OpenStax textbook. I didn't ask you to draw the tetrahedron, by the way, but I'm just drawing it. So electronic and molecular in this case are identical. The next question is, what is the orbital hybridization? What does that mean? Right? Well, again, Lewis dot structures get us started, but it doesn't explain why. It doesn't explain how molecules are going from, how we go from atoms to molecules. So we know that we have S, Px, Py, Pz. We know we have a total of 4 atomic orbitals available, in this case for the nitrogen. Those orbitals undergo a process called hybridization. It's an energy change. Essentially, the orbitals are recombined. In this particular case, we have 1, 2, 3, 4 chemical bonds around the nitrogen. And 1 or more of these could be lone pairs, and we'd still get the same result. So if we require 4 chemical bonds, or bonds and lone pairs around the central atom, that's going to be sp3 hybridization. Okay? We use the s orbital, px, py, pz. To contrast this, if we have a double bond, then we would only have sp2 hybridization. And again, this is something that we'll talk about this in class as we get into molecular orbital theory. But you really should refresh your memory. Again, go through valence bond theory. So this is called valence bond theory. And that gets you into chapter 7, going into maybe chapter 8 material. And it's very important because explaining how chemical bonds have formed, well, you start with atomic orbitals, and then you get to these hybrid orbitals. What we're going to really find is this orbital hybridization that we're talking about, it's actually the beginning of getting us into a more advanced theory called molecular orbital theory. So valence bond theory does have some very good uses in chemistry. Organic chemistry uses it all the time, of course. But we're going to see it's actually not the end of the story as far as how we combine atomic orbitals to make molecules. So that's something that's critical. The next question is the molecule polar or non-polar? All right, so what's going to define polarity in a molecule? And if we look at this molecule in 3 dimensions, well, we've got 1 oxygen, the nitrogen, and then 3 chlorines below it. Now, it's always good to kind of compare and contrast molecules. If we had methane, so methane is also tetrahedral. In the case of methane, all 4 positions are hydrogen. They're all equivalent. In this case, even though the carbon-hydrogen bond has a little bit of polarity to it, and again, if you go back to the concept of polarity, electronegativity, that should be ringing a bell, because the molecule is symmetrical, that means it's nonpolar. All right. If I do this, so methane is nonpolar. Let's say I do this. Let's say I put a fluorine atom here. It's still tetrahedral, but I've broken the symmetry. Now this molecule is polar. Right? Symmetry is going to be another concept that is absolutely critical in our understanding of molecules, and we're going to get into molecular symmetry after molecular orbital theory. So when I use that term symmetry, we kind of have an intuitive understanding of what that means, and we're going to expand on it, and we're going to really formalize it from a chemistry point of view. So this molecule, well, we've broken the symmetry of the tetrahedron. We have an oxygen here. Oxygen is not the same as chlorine, so there's going to be a difference in how the electronegativity is affecting this nitrogen. In other words, we've got 3 chlorines pulling on it and then an oxygen, and so that's going to create a dipole. If we make the assumption that the oxygen is pulling more on the nitrogen than the chlorine, then that means the oxygen would be partially negative and the nitrogen would be partially positive. And the way you can determine that is by looking at the electronegativity values. And let's say we got it wrong. Let's say it's the other way around. Let's say the chlorine is more electronegative than the oxygen. Well, that flips the polarity, but it doesn't actually change the fact that it is polar. So this, and we'll go through the details of this. So this molecule is polar. Again, 3-dimensional structure. We start with a 2-dimensional structure, and then we get to molecular geometries, VSEPR geometries, and that's what we're going to need for answering these type of questions. So chapter 6 gets us into quantum mechanics, starts building up the foundation of the atomic orbitals and electron configurations and the periodic table and so forth. Chapter 7 gets us into Lewis dot structures, and I believe VSEPR is in that chapter. And then chapter 8 gets us the more orbital hybridization, molecular orbital theory. So again, take the time, read through chapter 6, 7, and 8. Again, refer back to the email that I sent for the reading, and I believe I put some suggested problems on there. I'll continue to work through quiz 0. Again, I'm not going to put all of the answers, or I'm not going to put all the problem answers in YouTube format. Eventually I'll post an answer key, but for now, you should be, again, working through this, preferably, again, before the first day of classes, before the first night before the first day of classes. So again, this will pay off further down the line if you take the time and work through these.